Hello everyone and welcome to the next webinar series. This is our June webinar and we are conducting webinars every month. So please stay connected for our upcoming sessions. I am Aparna Deshmukh, Technical Director with Next, and I will be your moderator for today's session. We are excited to dive into our today's webinar titled GFRP bars as an internal reinforcement to concrete, advantages, misconceptions, and effect on greenhouse gas emission. A PDF of this presentation can be found out in the handout box. You can use the PDF to follow the presentation and take notes if you like. You may use the question box to ask questions during the webinar, and we will do our best to answer those at the end of the presentation. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 1 learning unit. Let's get started with a short description for our today's webinar. This webinar will focus on the advantages of using GFRP bars as an internal reinforcement in concrete structures and address misconceptions surrounding their performance. It will also highlight the environmental benefits and provide the real-life examples of successful GFRP reinforced projects, making it valuable for professionals interested in sustainable construction practices. Our learning objectives for this webinar are as shown on the screen. Now let's welcome and introduce our today's speaker, Mr. Borna Hajmiraga. Mr. Hajmiraga is a highly experienced engineer and CEO with nearly 15 years of experience in the fiberglass reinforcement industry. Currently based in Toronto, Ontario, Mr. Hajmiraga serves as the CEO of MST Rebar Incorporated, a GFRP rebar production facility. His work involves various thermosetting and thermoplastic resins, and he is recognized as one of the pioneers in pultruding a thermoplastic rod. Under his leadership, MST bar became the first fiberglass rebar to receive ICC approval. Mr. Hajmiraga is an active member of Canadian Standard Association, American Concrete Institute, and ASTM. Let's welcome Borna and listen to his presentation. Please take it away, Borna.
Hello, everyone. Well, thank you very much for the opportunity given by ACI. I want to take the opportunity to thank ACI and everybody involved in preparing this presentation. I'm going to start my presentation by talking about fiber. Sorry, just see if I can go to the perfect. We really, the topic of the presentation will be GFRP bars as an internal reinforcement. What are the advantages and some of the misconceptions out there and the effect of GFRP on greenhouse gas emissions. As a manufacturers, we believe in do it right and do it once to build the structures that would last long and is sustainable and resilient. Again, my name is Borna. I'm the CEO of MST Rebar Inc., a master degree in mechanical engineering and involved in ACI, CSA, and ASTM standard. In this presentation, I will speak about the cost of corrosion in US and Canada, some of the examples of corrosion, some of the benefits of the product, some of the project highlights we have done, and lastly, I'm going to talk about some of the misconceptions and some of the effects on greenhouse gas emissions by using fiberglass rebar. For those who have been in my previous presentations, there will be some initial slides that are very similar to my previous presentations. And on item number 5 and 6, misconceptions and effect of greenhouse gases, I will get a little bit more involved in technical aspects. A picture on the right side, as you guys can see, is an example of successful implementation of fiberglass rebar. MSD bar has been used in these projects, reinforcing these ports, very long ports from epoxy coated, traditional epoxy coated to fiberglass rebar, and the project was extremely successful, and it's supposed to last for many years. In Canada, we spend about $52 billion fighting against corrosion. Again, these are public information. This is not only related to concrete and reinforcement, but a big portion of that is related to steel reinforcement for concrete. In US, this number was more about $500 billion. Again, this is corrosion from steel pipes to tanks to to HSS and H-beam, all the way up to corrosion of the reinforcement. A picture at the bottom, you can see some example of the corrosion. Again, these examples or you can see it in everyday structures, and these are the problems we all have, and the problem is the corrosion of the steel reinforcement. Sometimes people ask this question, Borna, why do you keep talking about the corrosion of the steel? Concrete goes bad. Well, that's not true. Concrete lasts very long time, and we can see it from the history. Roman Empire designed the first bridge in 6 centuries, 1600 years ago, and that bridge is still there with zero sign of corrosion. Today, you build the bridge 15, 20 years later, the situation is really bad on those bridges. And the reason is introducing a material that's going to oxidize over time. And I always use the terminology of cancer in the concrete. You're giving birth to the concrete, and in the day of the birth, you're putting a cell inside the concrete that you're giving it a time limit. How to get rid of it? By introducing materials that will never last. Some example of the corrosion. You guys know this, but these are common examples of the corrosion: columns, barrier walls, parapet walls, bridge decks, roads. I mean, these are nothing new, and it's very costly. It's very costly to prevent these corrosions, and the repair and consequences are very expensive for the end users. Example of the corrosion, guys. I will just show you guys a lot of picture. These are, you definitely see them every day, from parking garages, slabs, and to all the way to really from bridges and roads. Also, just for everybody's information, fiberglass rebar is not the first attempt for civil engineers or structural engineers to fight against corrosion. This has been 100 years battle between structurals and mechanicals and all the end users of how do we get rid of corrosion. All the process that has been developed, in 1970s, they all delayed the corrosion. Why? That's when you put coating on the bar, when you play around with the chemical of the steel, all you do is you delay the corrosion. So you're never stopping that process. Also, fiberglass rebar is not a new materials. We have been around since 1990s, not us, our industry. And GFRP industry has grown because of the demand and the pull on the market. There has been a huge demand on the materials to fight against corrosion. So it's nothing new about fiberglass rebar, and we'll talk about that later. So what is the solution for all these corrosion? Is the materials that never corrode. Simple, and that's glass fiber reinforced polymer. The nature of the glass is the materials that will never rust. They can take a lot of alkaline and aggressive environments without showing any sign of oxidation. For those who doesn't know what's GFRP made of, GFRP stands for glass fiber reinforced polymer. And I'm sorry, these are, for some of you guys, you might have already know about this, but I have to do a little bit of introduction for those that are new to this presentation and the topic of GFRP. If you look at the picture on the right side, this is an example of a piece of rebar. I assume this is a 29 millimeter number 9 rebar Imperial. And if you grab this bar and you polish it and polish polish it under microscope, you will see the picture on the left side. Just for your information, this is about 20 micron. 20 micron is roughly about a hair diameter. So those fibers are about a third of your hair diameter. And the material that is going in between is the polymer or epoxy that is holding these fibers together and protecting them from environmental damage. So that's a little bit about fiberglass. So really a composite material is made by polymer, which consists of roughly 15 to 20% and about 85 to 80% to 85% glass content, which that's what you will see here. In one slide, I'm just going to quickly talk about all the benefits. I don't think I missed anything, but for those who doesn't know some of the benefits of the product, corrosion. So I talk about the corrosion a lot because you're buying a risk insurance by spending maybe by spending a little bit premium, which with today's market price of steel reinforcement and fiberglass, obviously when you compare it to epoxy coated and galvanized, you're definitely looking at very similar costing, if not slightly less. So really corrosion resistance is number one. Number two, weight. Material has a density of 2,100 kilogram per cubic meter compared to 7,850 kilogram per cubic meter of steel. So the material is about 3.5 to 4 times lighter than steel. Material MSD bar and products like MSD and obviously a lot of GFRP, most of them, they have a very high bond strength to concrete. Again, manufacturers varies the manufacturing process, but every product pretty much in the market meets the ASTM value, which some of the products out there, such as MSD, they provide a very high adhesion to concrete, which keeps your cracks smaller. There's a lots of benefit to it that we can talk about that later. Material is very easy to cut, so you can literally grab a hand grinder and cut the bar in 2 pieces without any spark, or very easy. So fabrication is very easy. On the other side, the material is beneficial because if you have a future opening, if you're designing a temporary retaining walls, or if you're designing, for example, in tunnel application, in TBM tunnel boring machines, at the end of the diaphragm, when you have the diaphragm and you have the tunnel boring machine cutting through, fiberglass rebar composite materials are very easy to cut through, and that's because of a non-isotropic material behavior. Fiber composite materials are orthotropic instead of being isotropic. So that means they're much stronger in one direction and weaker in the other direction. So the material can cut through very easy. Material is fire rated. This is misconceptions, which I'm going to talk about later, about how does GFRP stands fire and high temperatures. And material has been tested for over 3 hours fire rating. The materials can take, obviously concrete protect the fire, protect the rebar from the fire, and the material has been rated for fire rating. And I'll talk about that later. The test has been done according to ASTM, E119, and there's a lot of tests that are coming. They show that GFRP can be successfully used in buildings and structures with fire safety requirements. Tensile strength of the GFRP, guaranteed tensile strength of some of the materials that are ASTM qualified are roughly about 145 KSI. That's a guaranteed value. In fact, in our QC, when we break these bars, we are mainly more about 200, 210, 190 KSI. So as a manufacturers, we definitely want to put a factor of safety out there. So we pretty much dumb it down by 20%. And obviously, when you use ACI codes and other codes, you have more factor of safety. And at the end of the day, you pretty much use the same 60 or 40 KSI that what you have been using for steel. But it's all about factor of safety and public safety. Material has a very good fatigue strength under cyclic loading. The material can go under many cycles. The material can be cured by using, fresh water. So instead of fresh water, you can use salt water. There has been a lot of research by a good friend of mine, Dr. Tony Nani at the University of Miami, Florida Department of Transportation. And these tests are very unique and show that combining a secrete or an aggregate that can resist alkaline environments with fiberglass rebar, you can successfully use salt water to cure your concrete. Material, it does not conduct electricity, so you do not need to ground this rebar. If you're doing a swimming pool, MRI room, if you're doing structures that you're worrying about electromagnetic field, fiberglass rebar are neutral to electricity and electromagnetic field. Material also is non-conductive, which is very unique because when you think about a hot summer day, 70, 80 degree outside Fahrenheit, or 30, 35, 40 degrees centigrade outside, and the steel rebar can heat up pretty fast, which it's not fun to lift a heavy bar when it's super hot. Vice versa in cold temperature, when it's minus 30 degree, it's very difficult to handle those materials. That's one of the advantage of fiberglass rebar, is they do not conduct cold or heat, so they're very easy to work around. And there's other benefits about thermal break and other advantages we can talk about. Also, some preliminary studies that today I will talk about, really it shows that the fiberglass or composite materials are 75% less energy intensive compared to steel, and we use significantly less energy to produce this material compared to traditional reinforcement. So a quick question people ask, Borna, why do we have to use GFRP? First of all, the material is code approved, ICC, ASTM, CSA, ACI. There are different brands out there, and I highly recommend to everybody to do their due diligence before choosing GFRP. The structural engineers have to spec the properties of ASTM, the 8505. These are the codes that are out there, and really gives you guys the confidence that you're using a high quality product. The material reduce injuries at the job site. It's back injuries and other injuries at the job site, and the material is significantly easier to install. So these are really the 4 points that, in terms of end users, and end users have to think about when they want to choose their reinforcement for their structures. I will show you a couple of pictures where we have been using MSD bar, fiberglass rebar. GFRP has been used in caissons, piles, piers, columns, decks, slabs. Really, you guys can see a picture on the left side, heavily reinforced column caissons, number 10, 32, 35 millimeter bar with number 5, 15M rings or spirals around. So it has been used in a lot of heavy applications. GFRP has been used in bridges, in roads. This is all GFRP reinforced bridge, from foundation in the middle to columns to pier caps, retaining walls. Everything prefabricated to the job site, cut to length, bended. So very easy for the crew to install these bars and use them. It's a very cool video. I'm going to show you guys how light the material is. The material, this video is going to show you guys 25 pieces of funny enough, during recording this video, we really had to choose the skinniest guy at the job site to lift this material and move it around. That's 25 pieces of number 4 bar. One guy can carry it around and move them around the job site. More applications, 220 feet slurry tanks for biogas applications, animal waste, 40 feet high, pure ammonia and very aggressive environments reinforced with GFRP. Precast versus cast in place. Picture on the right side showing you guys a precast bridge deck. Picture on the left side showing you guys a cast in place. So there is definitely no problem using it in both precast and cast in place applications. Just show you guys how easy the bar is to lift and move around. Same way, like traditional steel, nothing changed. You tie them with the same material, you move them, you place them the same material. There is definitely no problem moving this material around. The material tied together, these are coated tied wires. People ask how we tie these together. Oh, we need significantly more ties. As you can see, you don't necessarily need to tie every corner. You skip one, tie the other one. So same way as traditional steel reinforcement, and nothing is supposed to change. Also, we have been using fiberglass rebar not only in new structures, but into repair and rehab work. Example of the corroded piles. This project was done in Panama City. In Panama, the main corridor bridge. The picture on the left side showing the corroded steel. It's after 15 years of, this is after 15 years of the construction date, and they use MSD bar fiberglass GFRP bars around the column and repair the structure with no issue. So it's not always brand new structures. You can also use it on repair work, and this is the condition after the repair. Yeah, so very interesting. More pictures of tying, pre-tying. People ask some questions. Can you tie these materials? Can you pre-tie them and move them? Absolutely, yes. You can, the picture on the right side showing you a precast facility for a water reservoir, underground tanks. Picture on the left side showing you guys some trench or some, simple trench or culverts. Residentials, we have done tremendous amount of work in residential works, from simple, footings and slabs to walls, 8-story, 9-story buildings. We have been using. There's a nice video here. I can show you guys this video about using fiberglass. So Aparna, if you can play that video. This video just showed you guys that you work with the material the same way as you do with steel. You tie them together the same way, you put them together. The workers, they treat the material the same way. Nothing is supposed to change. There are also some nice design softwares out there for some of the structural engineers that they are looking to design with fiberglass rebar or GFRP. Alter, S Concrete, and S Line has been incorporating ACI 440.11 GFRP-22 into their design software, and it's really at your fingertip. Some very well-known engineering firms like AECOM and EXPs and ExxonMobil, some of the big firms has been using these softwares successfully, and there is definitely some room to improvement there to add more softwares, but just food for thought for some of the structural engineers are looking to use these materials. So now we talk about all the introduction to GFRP. Now let's jump and talk about some of the major misconceptions that are out there. These misconceptions has been gathered to us by experience. People say, Borna, well, great materials, great choice, great durability, but fiberglass rebars are not ductile materials. They're linear elastic to failure, and this is a big problem. So I'm going to talk about that. The item number 2 is lack of fire. Hey guys, how about fire? How does the material would behave in high temperature and fire? Item number 3 is, hey, this material become brittle under cold temperature. How does the material would work in, extreme cold temperature? Item number 4 is just very common. People are saying, no, you can't use 1-to-1. You got to use significantly more reinforcement in GFRP because of serviceability. And I'm going to talk about that a little bit too. And the last item is, people ask, what is the real life expectancy of GFRP? I mean, what is the oldest structures out there? What is the real life expectancy of these materials? I'm going to talk about that. Let's jump for the first one. First of all, let's look at the definition of ductility. Let's look at question number 1. What is ductility and why is it important? Ductility obviously is the ability of the structure to go under large deformation and obviously sustain service load. I asked this question from every civil engineers. Guys, why do you need ductility? Number 1 thing is we need a sign of failure. We want to be able to see the concrete is failure. This is number 1. Structures manufactured with fiberglass can go under fiberglass rebar. They can go under significant deformation, and in fact, that comes back to the serviceability because you have to put more rebar to prevent that deformation. So, which I'm going to talk about it later. But we have done a lot of testing, and one of the testing we have done is actually showing you a beam made with MSD bar, and this beam is under 2 million cycle. This video actually recorded after 2 million cycle with over 24,000 pound force. Question: does this beam behave ductile? If you ask me, absolutely yes, because based on the definition of ductility, you're seeing a huge deformation on this slab. And funny enough, we could actually push this even further to have even more deformation on this beam, and we wouldn't be able to see the failure until you really push it hard and the concrete would crush by compression on the top. So now let's go back again and look at other applications. We have done a cantilever testing in-house, a balcony cantilever with 8 or 9 feet of cantilever, and we loaded to the ultimate. This is the ultimate load that the designer said, well, at that load, this balcony would fail with steel, would yield and would deform and would literally hit the floor. We loaded the same thing with MSD bar fiberglass, and we loaded to 1.8 tons. Forgot the forcing that we put there in kilopascal. I believe 196 pounds per square feet. That's how much load we put there. And if you draw a line, you should be able to see a decent deflection at the end of this slab. So question, is this ductile enough for you to see a sign of failure? Absolutely, because if you can't see those kind of deformation, well, you need a better eyeglass. you need to zoom in and be able to see that yes, this structure with fiberglass can go under huge deformation before failure. And again, I believe the definition of ductility is very important, or the definition of brittle material. So this slide is really unique because if I show you guys, if I explain the vocabulary, and I think this came from really a vocabulary, a definition, fundamental definition issue is, what is the definition of brittle material? Brittle material is any material that is linear elastic to failure. By that definition, both of these pictures that I'm showing on the left and right are considered brittle materials. Well, is the material on the right side brittle and the material on the left side brittle? So I think as a structural engineer and mechanical engineer, material science, we have to look at the definition of brittleness a little bit more careful when we're talking about the fiberglass rebar, because fiberglass rebar can go under a huge deformation, and that's what you can see on the right side. So that's number one, terminology. For the same reason that the material is linear elastic to failure, it actually makes it very unique in seismic. And we're going to talk about that. Currently, ACI 440.11-22 is not addressing GFRP in seismic. And obviously, the reason is our industry, they need to gather more information, more academics should get involved. And this obviously codes takes a lot of time to change. But some of the preliminary tests that has been done, University of Illinois, University of Toronto, Dr. Shamim Sheikh, Dr. Brahim Ben Mokraim, many professors have done many testing, and they compare steel to GFRP under seismic loading. And what's actually interesting is that the new terminology of self-centering, or what I would use a terminology as performance-based design, that you are walking away from energy dissipation method, it's actually a new era in concrete reinforcement by using GFRP. And as you can see, that the steel reinforced after the seismic load had about 4.85% residual deformation. A same reinforced concrete with GFRP had only 1.8% and was able to successfully go, over 5% drift ratio with no issue. This is huge because that shows that after the seismic, the structure went back almost to its original shape with very minor deformation, versus a steel, because of the yielding, was staying deformed. And I think this is a new era in civil engineering to use fiberglass rebar in seismic, and ACI codes and NEX and all the committee members, we are working really hard to implement this new system into the upcoming version of ACI 440. Number two, one of the second misconception is lack of fire resilience in GFRP. And this is very common because people say, Borna, material is plastic and material would not, is plastic based. Well, that's true, but before a material considered plastic, it should consider that 85% of this material has glass in there. And even at fire, after 2 hours, even the polymers start to degrade. The glass is not going anywhere. Glass has a melting melting point of even 300, 400 degrees higher than steel reinforcement. So we won't have any problem. This testing has been done in some very established organizations such as NRC, University of Queens. Many researchers has been involved in these tests, and they actually tested actual parking garage slabs with minimum cover concrete, and the material was able to sustain and achieve 3 hours fire rating with no problem. One thing you have to be careful when using GFRP, you have to make sure that the structure has been detailed properly, as the bond degradation is the main controlling factors and it's not the tensile or strength of the bar itself. So detailing is the key. This is the result of the test. As you can see, after 3 hours, the temperature was calculated according to ASTM E119. This is a 4-meter span of an actual parking garage, with 1.5 or 2 times service load, I believe, on top of that. So it was loaded more than what the actual service load is. And you can see both slabs was able to achieve over 180 minutes which is over 3 hours of fire safety. The next item is really, as I mentioned, detailing is the key. You want to make sure that the splice are not in the middle. You remember, anywhere you have the bond requirements, you want to make sure you create a cool zone. As long as your slab is over the support and you have minimum 200 millimeter of what we call cool zone, then that bar should be able to develop the full tension in whatever they're left out of the fibers after 3 hours of fire testing. Item number three is really one of the other misconceptions, or brittleness under cold temperature. People say, fiberglass rebar or GFRP at cold temperature, it does not behave well. And that's not true. This test has been done by Ministry of Transportation of Ontario. They have conducted a Charpy V-notch impact test. This test has been done in 2006 on number 5, number 8, and number 6. And the test was fairly simple. You create a notch and you do the different temperatures. So they did at the room temperature, they did at -20 and -50 degrees. And what's interesting is, as you can see, that the force was able to go. It was able to achieve a higher loading because the material actually gained some strength at the higher temperature, at the lower temperature. We also have done actual fire testing as part of our qualification in CSA SA-7. We actually put the bar in a nitrogen chamber at -40 degrees Celsius, as you can see, and we pulled them. And the strength retention compared to room temperatures was actually going higher. So this shows that 7 to 10% more strength at extreme temperature. So that's very unique. So this has been addressed, and there is no issue with that anymore. Item number 4, again, people say, yes, great material, but we need more reinforcement for serviceability. So let's look at serviceability. You have crack width and deflection, and you really have to control both for a successful design. Number 1, let's talk about the crack width. There are certain parameters in your design that control the crack width. When you calculate your crack width, it's very important to consider that the higher the bond strength you have in your reinforcement, and the better you transfer these shear forces from concrete to bar, your crack width stays smaller. So people ask, what if the crack width goes higher than usual? I always say it's not the end of the board, because if you remember, crack width, main problem with crack width is with steel rebar, because you do not want the steel rebar to corrode. What's the problem with fiberglass rebar that does not corrode? So, the code, I believe, on the next slide, the code really, the allowable crack for steel, I believe, is 0.5 millimeter, and for fiberglass is 0.7 millimeters. So in the code, we actually allow larger crack widths compared to steel. Also, the other thing about deflection, when you look at deflection, the new code, the modified Branson equation code that is in ACI 440, it's actually a much better code to calculate your deflection. And the other, again, going back to the discussion of why do you need to control the deflection? I had a great chat with a good friend of mine, Dr. Shamim Sheikh, regarding L/480. And, I was working with one of the consultant engineers in a parking garage, and they were designing these parking garage on L/480. And I said, hey, I don't know if you need L/480. You might be able to use L/360. And they said, no, we can't do it. We have to go L/480. So I was talking with my good friend, Dr. Shamim Sheikh, and he said, Borna, what's interesting? L/480 is for plasters and paints. This is a parking garage. There is no plasters. There is no paint. So remember, what I always recommend is, yes, follow the same number as the steel on serviceability and deflections, but also be more flexible to say, hey, in this case, I might be able to absorb a little bit, a few more millimeters. I know. And the other thing I said is, you're driving on a parking, and by steel you're getting 4 millimeter deflection, and by GFRP you will get 9 millimeter, 8 millimeter deflection. In some cases you won't even notice that. There are also other ways to go around it as well, is by reducing your cover concrete. You can increase your effectiveness depth of your slab. That's going to compensate on your deflection as well. So there are some ways to go around it, and you definitely don't need three times or two times more reinforcement. In some of the worst case scenarios, we have seen maximum of 30% increase in the increase in the reinforcement, which that was reducing the diameter and making the bar slightly closer together for crack control. That was it. So really, when you think about deflection and crack width, there are many ways to go around it, and as long as you're using a high modulus and good quality rebar, you're not no, you're not. The other thing that I have to mention, really, what's interesting is many structures that are out there are already over designed with steel. I'm not using the terminology over design. I'm going to use the terminology over safe design. That means that, structural engineers was designing this based on number 4, and for a factor of safety is putting a number of 6 in there. When you go ahead and convert some of those design from existing steel design to fiberglass, you will actually see that the number of the reinforcement won't change, and you are within the limits of, L over 240, L over 360, L over 480. So food for thought, just keep in mind that don't look at it as, oh, I need significantly more reinforcement. Do the calculation and verify how much more do you need, and you will be surprised to see that you don't need much. Item number 5 is really what is the real life expectancy of GFRP? Nobody knows. Nobody knows how long will it really last. As far as we know, as an industry, some of the oldest structure designed with fiberglass is probably going back to about 36 years old. Bridges in Virginia, and those bridges, I think Dr. Tony Nanny, is the president of ACI, and some of the other folks at different universities has done many deep analysis in some of these structures, and some of the reports that I have seen out there, they basically said, after 30 years, this rebar looks like the first day they put it there. There was no degradation on the bar. This formula was a research program that's showing you the relationship between temperature and aging in an alkaline solution of, between 12.6 to 12.8 pH level. Very, very interesting, because if you put this number in the formula, you will see that at 60 degrees Celsius, at about 150 days, that's about equivalent of natural age of about 100 years. And if you do 60 degrees Celsius at 300 days of aging, that's about 200 years of service life. Now let's take this and go to the actual testing that we have done in laboratories. This is the test result of MSD bar, I believe number 4 rebar, just for testing. And the reference samples was 1,266 MPa, and the condition was over 1,117. So about 90% retention after 90 days at 60 degrees Celsius. What's really, really interesting here is that in ACI codes, when you design a fiberglass, you use a factor of safety of 30. So that means, 0.55. That's a reduction factor for tensile strength because of the environmental impact. So that means that based on that formula and what the test has been done, the products based on those conditions and the factor of safety that is in ACI, would probably those structures would last about 1,000 years, 800 years without any problem. So again, that's just a joke to just to show you guys that material can last significantly longer, and on a preliminary data we can see that on bunch of test results that we have done. The second part of the presentation is just quickly talking about the reduction in greenhouse gases and reduction in greenhouse gas emissions. Before I really dive into this presentation, I need to do 2 definitions. I need to talk about the definition of sustainability, and I need to talk about what is resilience. Let's talk about sustainability. Sustainability is the intensity of the raw materials, your input materials. It could be energy, raw materials, and the way you process the materials. And also we got to look at the definition of resilience. Resilience means longevity, how long that material is going to last. When you calculate your sustainability, 3 parameters really control parameters. 3 parameters control sustainability, which is raw materials, transportation, and production. So let's look at again, a comparison to what the other industry has been doing. So before I dive into that, I want to talk about the lumber industry. Lumber industry out there is forcing lumbers to be known as the cleaner option against the concrete, which is not true, because when you look at certain projects that has been done out there, Washington D.C. Mass timber structure, these entire structure reinforced with lumber, and the challenge that our industry would see is that, first of all, trees are a great mechanism to eat the carbon dioxide. So by cutting down the trees, we are definitely changing the way our environment works, and trees requires clean water. Trees needs water to grow. So these are some of the stuff that really the steel industry, the lumber industry is really pushing harder and harder. So really, concrete industry, it's time for us to wake up and really take the sustainability aspect of our concrete, reinforced concrete, really, really serious. So when you look at concrete is extremely durable and but is extremely a unique material. Concrete can last very, very, very long. And so really, why don't we let the durability get in a way of that longevity of the structures? And the challenge today we have is the steel reinforcement. Concrete, this picture is a great picture because the reinforced concrete house was the only house remain after a tornado, after the heavy wind loads, and compared to all the lumbers and wood houses. So, but the only thing today is on our way is concrete really a durable materials? Can it last long enough? And the real challenge again is the steel reinforcement. So by using fiberglass, you're making the concrete a resilient materials, a materials that can really, really last long. The other factor that affects sustainability, as I mentioned, is transportation. When you talk about the sustainability aspect of the material, transportation is a lot more efficient, 300% less transportation, or I use 1 to 4. One trucks of steel, one trucks of fiberglass or GFRP versus 4 trucks of steel. So you're reducing a significant amount of greenhouses by transporting the materials. So this is a very nice slide because I was able to gather a lot of this information from different sources. They're recommending rebar is roughly about 15%. Lowest one I found was 8.5%, and the highest one I found was about 20-30% of the carbon emission inside a full structure. So if you're building a bridge, if you're building a building, between 8.5 to 30% of the carbon emission for the raw materials are actually inside the rebar. The preliminary analysis we did is actually by using the fiberglass, we were able to reduce those from 15 to 9.5, from 8.5 to 5.5, from 32 to 21, from 23 to 15, and from 15 to 12. This is very interesting because our industry right now, we have to take every aspect we can to reduce this 1% at a time. If you look at, and this is another interesting slide in this presentation that really showing you for the whole projects that using concrete and reinforcement, you have many elements. You have aluminum, you have other steels, you have structural steels, you have CMU blocks, you have the concrete, and obviously concrete is being some of the major highest carbon emitters inside your concrete structure. But also, if you look at the rebar is really almost in the middle of this analysis, which rebar have really significant impact on the greenhouses of that project. So really, by using a materials that is more sustainable, you're going to really take this 1% at a time. Obviously, our industry, we cannot go ahead and change dramatically these values. Tomorrow we say, hey, we're going to make a concrete that is, 1% carbon emission compared to 42%. No, obviously that's not possible. So what we have to do as an industry, we have to really go with the low-hanging fruits here. What are the low-hanging fruits? How do we take 1% at the time of those carbon emissions to make the concrete looks better out there? The other really important things that I have seen out there that people don't pay attention, and this presentation has been done once with a good friend of mine, David Lai, from Ministry of Transportation of Ontario. And this was very interesting because this analysis has been done by Ministry of Transportation. And the data shows that for every 10 minutes of car being idle, there's about 2.4 kilogram of carbon dioxide emitting into the environment. And when you look at some of these road construction or traffics or congestions due to the reconstruction that are caused by steel corrosion at the end of the day, you will see that by the time you add these carbon dioxide, how many cars are in traffic, and if you add 10 minutes of every car delayed in traffic, suddenly you will see a huge carbon emission happening on the other side that you never thought about it. You never thought about this aspect. And I thought this would be very, very useful to put it in a presentation to show everybody that there are other carbon emitters out there, that it's not only the rebar and concrete. People ask this. People say, Borna, after the life expectancy of the structure, we're just going to go ahead and take the steel and recycle it and reuse it. Well, that's not true, because if you look at how you recycle that rebar, there are 8 or 9 steps. Number one, you got to demolish the concrete. Number two, you got to move those demolished concrete into the recycling plant. Number three, you have to remove all those rebar from the concrete and transport those rebars to a recycle plant, obviously your closest one, which I assume it's not that close really, and you have to produce billets out of those rusted old bars. You have to put them back to the mill and produce rebar. So there are 6 steps you have to take before you can actually reuse that rebar. So it's not so green. The industry promoting it much better than what it actually looked like. And it's not as simple as, I'm going to go grab this and put it and melt it down and reuse it again. So keep that in mind. And the next one is, this process becomes so nasty sometimes because machines breaking down. When you crush these giant concrete with the rebar, this seriously puts a problem in the machineries. That's one of the reasons some of these owners, they said, forget about it. We can't do that. Just dump them at the sea level, use them and I'm sure you guys have seen dangerous piece of rebars sticking out, in beach near public areas. And one of the reasons is because it's so difficult to take the steel out and reuse it. So now you guys are going to ask, Borna, great, what about fiberglass? This short video, really, I had to ask a good friend really to create this video and show people how easy it is to demolish a concrete with fiberglass. So take a look at this video and see how.
Yeah, and then just kind of keep an eye on it.
That's a piece of concrete slab with minimum reinforcement. A bobcat is grabbing that and start to break it. So you can see how easy the material is to get crushed and So this is a great video because it shows that how easy the material is to get crushed inside the concrete, and what's important, what's going to happen after this is that concrete, that rebar will become part of your future aggregates, because as you're crushing that concrete, you remember 85% of this material is glass content, so they get crushed inside the bar, and they get crushed inside the concrete, and they get reused inside the concrete without even you notice. This is the last slide, really, to show you guys that as an industry, we are who we are. That means really we measure. We basically we measure what we can measure, and at this moment we really have to take baby steps of reducing our concrete carbon emission by all the low-hanging fruits. When you look at carbon emission as a tunnel, I like this picture of carbon tunnel vision, because when you look at the carbon emission as a point, that carbon emission impacts many things, impact poverty, impact education, impact health, impact the society, air pollution. So you got to remember, it is not only the carbon emission. That carbon emission is very important because it impacts the whole society. And all we can do at this moment is we can control what we can control by doing 1% at the time, reducing whatever we can do to make the environment safer. That's pretty much it. I mean, on the conclusion side, it's really we can really emphasize that GFRP can be used in extreme cold and fire and harsh environments. You do not definitely need significantly more reinforcement to add the serviceability, as we talk about it. GFRP and concrete really can last long together, and it's time for industry to take advantage of this good marriage in heaven between concrete and GFRP. Really, GFRP will definitely reduce the carbon emission at the beginning of the project, and if you definitely compare that to the traditional reinforcement, and if you look at it as a life cycle analysis, that number is significantly lower compared to steel. GFRP is not coated. There's a misconception. GFRP is not coated, so it does not degrade or corrode like steel. GFRP does not become brittle, as I mentioned, in cold temperatures, and GFRP can be safely used wherever there is fire applications. That's pretty much it. We can go on a question and answer. Thank you very much, everybody who is listening to me online, and I wish I was able to transfer some of the knowledge to you guys.
Thank you, Borna, for delivering an outstanding presentation and sharing your insight with us today. Yeah, let's move with our question answer session. Our first question is, can these FRP bars be bent? Do they have to be heated up to bend?
That's a good question. Fiberglass rebar cannot be bent on job site. And mind you saying that you don't, as a structural engineer, as an owner, you don't want the people to bend the steel rebar on job site. Yes, some minor modification maybe, but because of the quality control aspect and tolerances and cover concrete, you definitely don't want people to. So yes, it cannot be bent on a job site, but I don't think anybody would see that as a disadvantage. In fact, a lot of owners, they like the fact that you cannot bend the rebar on job site, and everything have to be quality manufactured inside a factory. So there's no heating process. You cannot heat the bar and bend it because the material are thermoset. Thermoset is the crystallization of the polymer. When it sets, it cannot be reversed. That's one of the reasons you cannot post-form the material. There are technology out there that you can use thermoplastic, but they're not coded and they're not approved product yet.
Yeah. Our next question is, what are the downsides to use GFRP bars?
That's an excellent question, and I have been asked that question many, many times. And to my knowledge, there is no downside other than when you use a fiberglass rebar in your projects, you might need a slightly better planning. That means you want to do a proper shop drawing. You want to, do a proper shop drawing, send your shop drawing to the engineer once it's approved. Obviously, a modification is a slightly more difficult compared to steel. That means with a slight better planning, you should be able to use GFRP successfully in your project without any issue. So, good question. So far I have never heard any negative things other than sometimes people say, "Oh, I get fiberglass slivers in my hand." I'm sorry, you get wood slivers in your hand when you carry wood as well. So hey, wear gloves. Be responsible when carrying the material around, and there is really no downside to use it.
So our next question is again, it's on bonding strength. So for GFRP, the development length needed to transfer the yielding force to the concrete is higher than the black steel with the same diameter based on CSA S6 standard. So as the yielding stress of GFRP is higher than black steel, is it reasonable to need more length of to develop the yielding force? So what are your thoughts like on the real life project, and do
Excellent,
we need more
excellent.
research? Yeah.
Excellent question. Excellent question. Not all fiberglass rebars are manufactured equally. So this is a very important question because every manufacturers have a different surface treatment. You got to remember, is the development length of a smooth steel rebar same as the ribbed rebar steel? Definitely no, because of the bond strength. So that bond strength plays a significant role into your development length. MSD bar, product like MSD bar, what we call the continuous integrally ribbed rebar, where the deformation on the surface is a continuous deformation, and because of the Poisson's ratio. So let me go back again. Code trying to generalize all the GFRP. Code is always a code and want to cover all the products in the market. Different manufacturers have different test results that can provide to structural engineers to show that their development length can be different. In fact, based on experience and the test results we have on MSD bar, we have had most cases, slightly more than slightly, or you know what, almost half the development length of the steel, because of the bond strength. And the second criteria is Poisson's ratio, something people forget. And because when you graduate from school, you forget about the topics you learn. But Poisson's ratio is very important. Remember, steel has a higher Poisson's ratio compared to GFRP. What does that mean? That means when you grab a piece of steel and you pull it under tension, as soon as you pull it, it reduces the cross-sectional area. This is one of the main reasons you got to create the 90-degree or hook bar to develop the length, to develop the strength on the bar. Fiberglass rebar has a very low Poisson's ratio. That means under a significant tension, it does not lose that area. When you combine that to an aggressive surface deformation, you will suddenly see that it's a huge bonding between the concrete. We do have a lot of third-party test results. So whoever asked this question, I strongly recommend them to reach out to me, and I'm more than happy to share some of these test results that show that actually the LD of good products out there with good bond strength can be about half of those with steel. That's very interesting.
Great. Thank you. Our next question is, how do you connect 90-degree corners and bend rebar to L and U shape?
Very simple, overlap. We always recommend 40 times development length, as a rule of thumb, 40 times diameter of the bar. You splice them together and you tie them together. So we always recommend, if you have a significantly long bar and you need a hook at the end, you use 40 times diameter of the bar with a hook, splice it to a length of a straight bar, and that is a very safe practice. So 40 times diameter of the bar. Obviously, different manufacturers have a different lap lengths, and you can definitely reach out and get those lap length tables. And we have the MSD bar has its own table, and you can definitely use them very safely.
So our next question is, if bond strength is higher, then why is it easier to deconstruct versus steel?
If the bond strength is higher, I got to understand the question a little bit more. Can you repeat the question again?
Yeah, the question, it says the bond strength is higher,
Mhm.
then why is it easier to deconstruct versus steel?
Oh, I see what you mean. So we talk about the cutting the bar. Well, so remember the isotropic and orthotropic materials. Fiberglass rebar is very strong in one direction, that is the length of the bar, and it's weaker in this direction. So bond strength has nothing to do with with breaking it, because that's really I would say it's a combination of shear and being an orthotropic material and the aspect ratio of the fibers. This is one of the reasons the fiberglass rebar is much easier to cut. However, when you're trying to pull the bar, because of the fibers direction, that's you get so much stronger strength in that bar. So I can't correlate bond strength. Bond strength is really comes from surface deformation and what is your surface deformation, or what is your surface treatments. Certain manufacturers are sand coated, certain manufacturers are grooved where they grind the bar. So different manufacturers have different process, and really the bond strength comes from those surface treatments. That's yeah.
Yeah, we have quite a many questions, but we might not be able to take all of them. We have already passed to the last question. We will go with, um, you briefly mentioned alkaline deterioration during service life approximations. How accurate would you say the accelerated testing is when compared to real life alkaline deterioration?
That's an extremely good question. In fact, the accelerated aging test we have done, or we do according to ASTM and CSA, is significantly more aggressive than real life. And this is one of the reasons that some of those structures, as I mentioned, after 35 years of in service life, they barely see any reduction. I mean, it's like the first day they put them in. Really, so those testing we do in the lab are very aggressive. And in fact, in real life, you don't see those kind of conditions. Yes, you might see it in that biogas tanks I mentioned to you. You might see it in the sewer system or some precast applications. And those are really, I mean, really what's interesting is when structural engineers are asked to design those water treatment plants, you guys or structural engineers does not design it like a regular structure. You guys design that based on crack tightness or water tightness. So you need significantly more reinforcement there to make sure your cracks doesn't open up. This is one of those areas GFRP going to shine, because you don't care about those crack widths anymore. So you can design it the same way, not worrying about, durability of those structures. Unless you really don't want to see any water penetrating, then yeah, you can definitely do your crack tightness. But unless, again, if it's a water and animal waste or gas, or that's, you definitely have, unless you have a really highly aggressive chemical in those tanks that you don't want any leakage there, then you can definitely, design it based on a crack tightness or water tightness. So to answer this question, really, the durability of this material are very, very high. It's much higher than what they actually going to see in real life structure.
Yeah, I agree with
And,
you.
and, 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 and and to answer that question, fiberglass industry, it's not a new industry. As a mechanical engineer background in pipes and gas, guys, for those that are online, you really have structures out there, tanks that, fiberglass tanks. The entire tanks is fiberglass with no concrete in there, with no rebar, and those tanks are, they use them in lithium refinery, very aggressive, and extremely nasty condition with, existence of sodium chloride, hydrochloride, acidic environments and high temperatures. So material is extremely durable. Thank you.
Thank you so much, Borna, for answering all the questions. And we really appreciate your presentation. Thank you.
Thank you very much, everyone, and have a good day, everyone.
So this ends our question answer session. We really thank all of you for joining us today. We appreciate your participation and engagement, and we look forward to seeing you in our upcoming webinars. Please visit aciuniversity.com to see topics for our upcoming live webinars. Some of them are listed on the screen. Also, please remember to fill out a brief feedback survey that you will see as we exit the webinar. If you are looking for continuing education credit and were unable to join us for the duration of the live webinar, be sure to complete the online quiz at aciuniversity.com.